Hi everybody, welcome back. I want to finish up this last video dealing with the combined gas law. You're looking at the slide where you see all of the four basic gas laws: Avogadro, Boyle's, Charles, and Gay-Lussac. If we were in class, what I would normally have you do is I would give you ideal gas law, which you see right here, and then I would ask you to take the working formulas for each of these four and see if you could come up with a single formula that allows you to keep everything together or put everything together. It's a challenge, and most students are able to do this, and the whole goal of this, since we don't really have time to do it, would be to find a way to put everybody except for R on the same side. So what are you going to do? You're going to have PV, and you divide by the N and the T, and you're going to get R. Okay? So what I want you to be able to do with this is for you to be able to see within this section these individual gas laws. All right? Now the way we do that, the best way we do that is to go ahead and say, let's have a before and an after. Because remember, R is also pressure volume divided by moles and temperature. So what we end up with, because R, that's how we made it, pressure, volume, moles, temperature, can be on this side. So instead of standard conditions, there are other conditions. Right? So I just want you to understand it all comes back together. And I may not have explained that right, but again, not being together with each other, it's harder to be able to do that. But let's go ahead and kind of go through this quickly as we can, and then we'll do a couple problems. So each of the basic laws, Avogadro, Boyle's, Charles, and Gay-Lussac, they only look at two of the four factors. They either look at volume and pressure, volume and moles, which is Avogadro, pressure and temperature, which is Gay-Lussac, and volume and temperature, which is Charles. If we put more than two of them together, we call it the combined gas law. Now the one thing I will tell you is very rarely do we ever include moles. Most of the time with combined gas law, the only thing you're going to be talking about are pressure, volume, and temperature. So let's look at this, and you'll see what I've written here is basically what you see on the screen. But what I'm going to do is we're going to actually have a ones on this side and twos on this side. Now I'm going to go ahead and remove the N just to make it be the same so that you can actually see the relationship. Okay? So this is where I generally give you the challenge. And I'd love for you to pause this and to see if you can find Boyle's law, Charles' law, Gay-Lussac. Obviously I just took out Avogadro because moles isn't there. But see if you can find them within this equation. Right? If you want to do it, pause and come right back. Alright, so I don't know if you paused or not, but here we go. Let's find Boyle's law. What is Boyle's law? Anybody remember? Well, Boyle's law is pressure volume, and if you hopefully can see this, you can see Boyle's law right there. Boyle's law is P1V1 equals P2V2. It's right there, and we set it up from ideal gas law. All right? What about Charles' law? Charles' law is volume and temperature. And look at there. V1 over T1 equals V2 over T2. And then we have Gay-Lussac. And Gay-Lussac is pressure and temperature. And Gay-Lussac is right there. So every one of these laws fits from ideal gas law. We can use it in the combined gas law. And it just It just makes sense to know how they all relate to each other. Okay, so we are now at the place where we have to actually work some problems where we're not going to be just looking at 2 conditions, but we're going to be looking at 3 conditions. 2 of them are changing, and we're looking at what happens to the third one due to changes. So we have a before, which are the 1s, and an after, which are the 2s. Okay? You're going to have a factor that is missing. You will not be using your gas law constants. Rarely do these include moles, but then you'd be using Avogadro's law. Volume has to be consistent. It doesn't have to be liters, but if you're starting with milliliters on one side, you have to have milliliters on the other. And the reason why you don't have to have liters is because we're not dealing with R. Temperature, on the other hand, has to be done in Kelvin. Alright? So you got kind of sort of the rules. Let's see what we can do. Alright, practice problem number 1. First of all, let's just find out what we've been given. Alright, we have 2 liters of gas. That's going to be volume 1. Alright, what else do we have? We have 35 degrees Celsius. Oops, guess what? That's T1. But let's go ahead and change that over here to, to Kelvin, and we have 308 Kelvin. Alright, so what else do we have? And we have 0.833 atmospheres, which is going to be P1. So we have V1, T1, and P1, alright? So what then do we know? It's asking, we're saying it's brought to standard temperature and pressure. Well, what is standard temperature? It's going to be number T2, and we know it is 273 Kelvin. What is standard pressure? Well, since we're already dealing with atmospheres, we might as well deal with atmospheres, and we know that standard pressure in atmospheres is 1.0 atm. So it's asking for V2. So I'm not going to go through the solving for V because I don't use it this way, but you will see on the screen of the slide how you would rearrange to solve for V. Personally, I just like filling in the formulas. So let's do this. We're going to go 0.833 atmospheres times 2.00 liters. We have T1 at 308 Kelvin. We have P2 at 1 atmosphere. We have V2, which we don't know, and we have T2, which is 273 Kelvin. Guys, this is just a, it's a proportion. It's a fraction. You can do this the way you do everything else with simplifying this side if you want to. Then whatever you do to this side, you're going to just simply put 273 here, 1 atmosphere there. These guys cancel. Look, atmosphere cancels, Kelvin cancels, and all you got is liters. I don't even know that I would take the time to do that. I would just multiply, divide, equal. But that's who I am, so this is just basically doing the math. I know it's messy, but now you have math to do. 273 times 0.833 times 2 divided by 1 divided by 308, and you're going to get volume 2 is equal to 1.48 liters. Now, if it makes more sense to you to do this without listening to me, please look at what's on the slide or listen to me again if you need to. There's lots of folks out there on the internet who can give you some good information. Okay? Alright, so let's do this another problem. Alright, I'm keeping up my original formula here. We're going to put all of these over to the side. And we're going to find out what we have and what we don't have in our... Alright, so it says a small research submarine has a volume of... Alright, V1. This is 1.2 times 10 to the 5 liters. Internal pressure of 1 atmosphere. And an internal temperature of 15 degrees Celsius. Alright, so we got to take our 15 degrees Celsius and we're going to have to change that. We're going to have to add 273 to it, and we're going to get 288 Kelvin. Alright, what are we trying to do afterwards? What do we see that's an after? If the submarine descends to a depth where the pressure is 150 atmospheres, and the volume is 767 liters, we're asking for what's the temperature. If the hull of the submarine breaks. Okay? So I'm not going to rearrange. I'm going to put my numbers in. I'm just going to put my numbers in so we can see what they look like. P1, 1.0 atmosphere. I'm just looking at my formulas. What's V1? 1.2 times 10 to the 5th liters. Alright, what's T1? T1 is 288 Kelvin. Alright, what do we have over on this 2 side? We have 150 atmospheres for P2. We have a volume of 767 liters for P1. I'm not going to be able to show this to you because I just drew over. So let me see if I can fix this. There we go. And what are we looking for? We're looking for T2. Alright. So when I talk to you about multiply, divide, equal, what I'm going to do is this. I'm going to take the two of those, 150 atmospheres times 767. I'm going to take the two of those things. I'm going to put in my calculator 150 times 767. I am going to multiply that by 288. I am then going to divide by 1. I'm going to divide by 1.2 times 10 to the 5th liters, and it will equal my T2, which is 276 Kelvin. I promise you this works. Now, rewatch this. Take this side, the upper right, multiply 150 times 767 together. Put it in your calculator. Let me even see if I can figure out a way to get my calculator to show this up. Alright, here we go. 150, I'm not going to put the decimal place in, times 767. I'm going to multiply that by 288. I'm going to divide by 1. I'm going to divide by 1.2 e to the 5th. And I'm going to hit enter. And I'm going to get 276.12. This is a very easy problem that does not require having to rearrange it. It's a proportion statement. And so what's on the top gets multiplied with on the bottom, divide by across here, and you're going to get that you're going to get your answer every single time without having to rearrange any equation. Just use what you're given. Alright, 14 minutes. I really didn't want to do that. Anyway, you got 2 problems here. Please come back and look at them. The problem sets will be assigned following up. Alright, talk to you guys later. Bye-bye.